All right. Okay. Today kind of marks the last day of our intro to ML series. So just to do kind of a review of the last two lectures. So kind of the very first thing we covered was the difference between AI, machine learning, deep learning. So this should be our third time covering this. Um, Again, deep learning is kind of the most narrow subsection of all of these fields. And it's kind of the unifying goal, though, like across AI, ML, and deep learning, is that we want one kind of blueprint, one algorithm that could, in theory, learn to model any type of data, right? So what I mean by that is like we could have like regression, classification. We want one type of model that can solve these problems, right? So the first lecture and a half, we covered the perceptron, right? We learned how to do classification and regression, both supervised learning problems with regression, or sorry, with perceptrons. Perceptrons have weights and biases, and those are things we can pick ourselves. We can tune them ourselves. The idea is that we pick the right weights and biases to make our function learn, to make our model learn to fit to any data, right? We could ideally learn any pattern if we choose the right weights and biases. But we realize pretty quickly that this perceptron is just y equals mx plus b. It could only really model linear relationships between each input feature and each output. Remember, input features are kind of these columns, right? So in this case, when we're modeling rainfall, we have three features: humidity, temperature, wind speed. So yeah, we have one weight per feature, and we have a single bias per perceptron unit. Right. And again, we can't model nonlinear relationships, and we didn't really have a good way of picking weights and biases. If you remember, I was kind of on Desmos, kind of just like playing with the sliders, hoping to find the right fit. Okay, in our second lecture, we kind of addressed that issue of nonlinearity or unable to fit to nonlinearity by introducing this idea of a neural network, right? So each of these gray boxes in that one blue box, those are all, well, the single perceptron. But when we have multiple perceptrons feeding together in a network, we call those neurons. Again, internally, a neuron or perceptron are the exact same thing. We just call them something different when it's in a neural network versus when it's standalone. Right. So in our neural network, we have our set of inputs. So again, three features, right? These green circles are just, you know, modeling our inputs. We have our hidden layers, and again, these are just interconnecting neurons. Remember, neurons always feed forward, right? They never feed backwards, or they never feed in between each other, right? So the data flows forward. And then we have a final output layer, and again, that's another neuron. The only difference is that the activation is different, right? So what is an activation function? Well, just by having, neurons feeding into each other, that doesn't guarantee nonlinearity, right? The ability to learn nonlinear relationships. By having each neuron use an activation function, a nonlinear activation function, we can then guarantee that idea of nonlinearity, right? So again, activation functions have two purposes. One, if they're in these hidden layers, right, we might pick something like ReLU, right? Yeah, ReLU down here. Can anyone? Well, it's right there. It zeroes out any negative value, but keeps the positive value the same, right? So we might use something like ReLU to again learn nonlinear relationships in our hidden layers, and in our output layer, we might even have a activation function, right? All right. Can someone remember if we're doing like classification with multiple output classes, like predicting rain, snow, or neither, right? Three output classes. What activation function could we use that we covered at the end of last lecture? Anyone? All right, we would use the sigmoid activation function. I might have to do a review of that at the end. Okay, so this addresses the issue of learning only linear functions, right? The combination of activations and neural networks. So how do we actually pick our weights and biases, or other words, our parameters, right? Our weights and biases together are called parameters. Well, we have this idea of training, right? Where we first randomly select our weights and biases. We do something called a forward pass, where we try to we just send each data sample through our neural network, measure how badly we did. In the beginning, we'd probably do very badly, right? Because we have random weights and biases. That metric of error is called our loss or loss function. And then we use that loss function to update our weights and biases in a process called backpropagation, right? And then we can then evaluate our model once we're done with this whole training process by comparing our test and train losses. Remember, we want to better evaluate our model, we usually split our data set into a train set and a test set. Does anyone remember, is the train set bigger or is the test set bigger? Just raise your hand and say it or just say it out loud. Train set, right? We want to give our model as much data as possible to learn from, but we still want enough test data so we can get a valid accuracy metric, right? And again, you don't just have to use accuracy or the number corrected divided by the total number of data samples. You can use precision recall, area under the curve, and so on. Okay, again, our forward pass is in our very simple neural network. We have one neuron with one weight, one bias, and array loop, and one output neuron with a single weight and bias and no activation, right? It's a very simple neural network. We could calculate the loss here. In this case, the true output was 3. Our Y prediction was 1.8, very bad. And in the process of backpropagation, we calculate the gradients of the loss. So again, in this case, our loss was the predicted loss minus the true loss squared. Does anyone remember what this loss is called? Ignoring the 1/2. Mean squared error, right? It's the error, which is Y pred minus Y true squared. The reason why it's mean is, well, normally we take the average of this across multiple data points. In this case, I only have one data point, so no averaging. Okay, thank you. So again, we have that loss, right? And then we want to work backwards to update all of our weights and biases, right? So in this case, I'm updating W2, right? So this nomenclature, hopefully this is review. This is the partial derivative of the loss with respect to the sec to weight 2 in red. So you should hopefully remember that we use the chain rule. So in order to calculate what this is, it's the derivative of the loss with respect to the Y pred times the derivative of Y pred with respect to W2. So we have this chain. You can imagine if we're calculating the gradient of something a lot further back in our neural network, like W1, that chain of derivatives is a lot longer, right? But it's the same process. Okay. And then this is the formula. So W2 minus the learning rate, that's this little fun symbol over here, times, well, that gradient. So again, does anyone remember why we have a learning rate? Why can't we just directly subtract the gradient from our weight?
Because you like over subtract.
Sorry?
You like over subtract.
Exactly. You might overcorrect in that direction and start off with go to a W2 that leads to a worse value, right? By having a very small learning rate, that guarantees we take little baby steps towards the right answer. Okay. All right. So again, review of training. We're kind of done. Like we've covered most of the key conceptuals. This lecture is going to be covering okay, so we know what backprop is, we know what training is, we know what neural network is. How do we make this more practical? Like how can we actually put this in code? How can we build this ourselves? So the first step in this process is kind of reframing this idea of a neural network in terms of matrix computations. Before I do that though, because it's probably going to get a lot confusing if you don't have a solid grasp of neural networks. Does anyone have any questions about forward or backprop? Or how data feeds into each other? All right, perfect. Okay, so review of matrix multiplication, by the way, this is kind of like a mini thing aside from independent deep learning. So matrix multiplication is, again, we have two matrices. So imagine if you're not familiar with matrices, that's a grid. So in this case, we have a 2x2 grid, right? Height of 2, width of 2, right? So I've denoted the dimensions as m by n. So height of m, width of n. And so if you take the product of two matrices with these dimensions, the output matrix, your output would be a matrix, would have these outer dimensions, right? So a good way of remembering it is the output dimensions are like the leftmost dimension of the first matrix and the rightmost dimension of the second matrix, right? So I'm going to work through a quick example, right? So how do we take the matrix multiplication of this matrix A and this matrix B, right? So again, our output matrix would be 2x2, right? Because this leftmost dimension of A is 2, rightmost dimension of B is also 2, right? So we have a 2x2 output matrix. So to get the value of like the ith element on the ith row of the jth column, so this top left value right here, you would multiply the ith row of A by the jth row of B. So in this case, we would take the first row. So, if we wanted to get the top left, so the 009, the 00 value, that would be the 0th column. We're doing zero indexing, by the way. You guys, hopefully if you've taken like 110 or 111, generally C has to be zero index. So if that's confusing, just imagine that's like this 0 is 1, right? 0 is our first thing. So we take our first row, multiply by our second column, by the first column of B. So that's 1 times 5, 2 times 7, right? Okay, and that gives us 19. So again, if we want the first row, second column of the C matrix, our output matrix, we would again take the first row of A multiplied by the second column of B, which would give us 50, or sorry, 22. Got my stuff mixed up. Yeah, I think I copy and paste the same calculation, right? That's my bad. But you kind of follow that calculation, right? You take that row on the A matrix, multiply by that corresponding column on the B matrix. Does anyone have any questions about matrix multiplication? Nope. All right, let's keep moving. So why do we want to frame this as a matrix multiplication? Well, the nice thing is that you might have noticed that we did those 4 calculations, right, for those 4 elements of our output matrix. Well, we kind of did them in parallel, right? Like each calculation was not dependent on the other calculation. So we could, in theory, run those individual, like these lines of calculations in parallel, right? So you guys may know that deep learning really became a thing in the 2010s, right? Why not earlier? The reason is largely because of compute, right? So the advent of GPUs allowing us to run these like simple bits of code in parallel is what really made machine learning viable. All right, so hopefully you guys may have seen this. NVIDIA brought down the Mythbusters. You guys know what the Mythbusters are, right? All right. So this is kind of illustrating the concept of a CPU versus a GPU. CPU being a graphical processing unit. All right. So the first demonstration is an analogy of a CPU. So they're trying to draw a smiley face, right? So notice it might be a little bit hard to see, but the robot arm's like shooting like the paint bullets one at a time, right? It's shooting each bullet, it's hard to tell, but like fairly fast, but it's still one at a time, right? And then to kind of keep doing that until they get a smiley face. Yeah. Yay, right? So we drew a fairly complex picture, like one kind of instruction at a time, right? Now a GPU, so they take some time unveiling it, but so oops, sorry. Okay. Right. So now they're trying to, whoa, that was kind of fast, right? They kind of shot all the paint bullets at once to construct, in this case, a far more complex image, right? In this case, like a, like a very discrete Mona Lisa. Okay. So, so the idea before we kind of break down those differences, I think it's important to understand like the rough high-level architecture of a CPU and like kind of in a GPU. So there's kind of 4 key building blocks you should know. So the first is an arithmetic logic unit or an ALU. So this is what's really doing the math inside of your computers, right? So all of you guys have CPUs on your computers, and all of you guys have a reasonable number of ALUs, right? So this is your multiplication, addition, subtraction. That's where that's happening, right? Your control unit is kind of the brains behind this. It's figuring out what order to do your operations. For example, like when you're running Chrome, right? It's figuring out all the different like assembly lines that should run, in what order, what things to pull from memory, what things to send to the ALU, and so on and so forth, right? The cache is, don't confuse this with RAM or anything else, but the cache is like small blocks of memory nearby your CPU or like inside your CPU that can be quickly accessed, right? So a CPU kind of has this very big, beefy control unit, right? That means it can handle really complex tasks, such as, well, handling your entire operating system, running, like if you've written code, running your code, right? Python, C++, Java. And it has some of these, a couple, but very beefy ALUs, right? Each ALU can run very fast, but well, you don't have too many of them. And you have this cache, like you have a very large cache that's split into a few subdivisions. But the point is, you have like one or a couple very fast caches, right? So with this structure, a CPU is really good at running a couple of complex instructions fairly quickly, right? Again, we have a couple units, like a couple ALUs that are very strong, right? Now a GPU, a GPU kind of is completely restructured differently, right? You might notice that we have a ton of ALUs. In modern day GPUs, you'd have like thousands and thousands of ALUs, right? And each cluster of GPUs, in this case, row of GPUs, has its own control unit and has its own little cache. These control units are like significantly weaker than that of a CPU, right? It's because we have a ton of them, right? We have like one per row. So these control units um, are really only capable of like running like very simple things, like maybe like one function in Python, for example, or like multiplication, right? Very simple instructions. And we have these very small caches. So all the ALUs in this one row share from the same cache, as opposed to like in a CPU, like you have this one beefy process that like can very quickly put stuff in cache and take stuff out of cache. Okay, so why am I talking about this? Again, a CPU has a few powerful ALUs and a very, very strong, usually singular control unit, while a GPU has a ton of ALUs clustered in rows or groups, and they can handle many simple tasks in parallel. That's kind of the key thing here, right? Like you can kind of see this row structure, right? We can handle many things in parallel, many simple things in parallel. So back to our matrix multiplication, for example, right? Again, if we could somehow represent our neural network in terms of matrix operations, right? Well, we could do this matrix operation very quickly. Each of these lines, each of these four lines could be done all at once in parallel, right? So in other words, in constant time, if you know of what runtime is. Does that make sense? So again, in this case, we have a very simple 2 by 2 matrix, right? That's not crazy. Your CPU can like probably do this in parallel, right? But in reality, think of ChatGPT, right? They have billions of weights and biases per layer, right? Like per layer, right? So that's a billion by a billion, right? So what they CPU could never model that, right? It would wreck your computer. It would take years to run. A GPU, right, with its thousands and thousands of ALUs, could run that stuff in parallel. Does that distinction make sense? All right. If we have any upperclassmen here, Professor Advait Jog covers this in his class. Parallel computing is very interesting, but that's the most parallel computing that we're gonna do this semester probably. Okay. So again, here is a very simple neural network with 3 neurons. How can we represent this in terms of matrix operations? Well, we can actually represent our entire input, so this entire input layer as one matrix, and this entire hidden layer, so this first hidden layer, as a second matrix. How do we do that? Well, so we could just make a 1 by 2 matrix for the modeling the input layer and a 2 by 2 matrix for the 2 by 2 matrix for the hidden layer, right? So this first row this first column, right, refers to the weights in the first neuron, and the second column refers to the weights of the second column, right? So again, if we kind of do that matrix multiplication this time, times of x times w, we'll get, okay, so 2 times 0.5, 2 times 0.5 plus is 1, and then 3 times minus 0.4 is minus 1.2, and we get minus 0.2, right? So we can model the entire layer of the hidden layer and the input layer as, well, 2 separate matrices. Okay, so our outputs of those 2 computations is minus 2.9, and then we add the biases from the 2 separate neurons, right? So notice that we're kind of like combining the 2 neurons almost, right? Like we're not really keeping them separate, right? Like this like one weight matrix represents 2 neurons, right? So we could scale this this layer for as long as we want. All we would be doing is making our weight matrix longer and our bias matrix longer. Does that make sense? So no matter how many neurons we have, this is still just like a matrix operation of 1, 2, 3 matrices, right? So again, this could be done in parallel with the GPU very, very easily, right? You can imagine if you're trying to do this like with a for loop iterating through each neuron, you can imagine that computation time would build up, right? And this time in this case, you could do everything in constant time if you have a very beefy GPU. All right. And then we pass the outputs of both those neurons into our ReLU. Again, it zeroes out a negative input while it's, okay, that's a typo. Should be 0.8. It doesn't modify the input. Yeah, that should be a 0.8. Okay, so we take the outputs from this layer, so this first hidden layer, and then we feed them into our next layer, right? In this case, our next layer has a single neuron. So in this case, our should be 2 by 1 in this case. Sorry, I was fixing up the slides before this, so I have some typos. Yeah. But again, since we only have one neuron, we have a pretty small matrix, right? Just one column. Okay, and so in this case, 1 by 2 times 2 by 1 gives us a 1 by 1 or a single value as output, which checks out, right? That's the final output of our neural network. So in this case, our final output is minus 0.44. So you could assume we're doing some regression task, right? Okay. Any questions about treating a neural network as a set of matrix operations?
Should there be something that goes in that blank space there, or is that?
I guess technically I should slide that up, I guess. Yeah, that's just like a placeholder for the calculations.
Okay.
Yeah. I meant to be like the intermediary value of x of t times w equals that value plus the bias.
Okay.
So yeah, I should probably just slide that up. So something I've been skimming over is the x to the t. Can anyone guess what the t means in this case? Transpose, right? So what is a transpose? Um, it's in this case, it's fairly simple, right? If we have a 2 by 1 matrix, it just rotates it to be 1 by 2, right? So the reason I kind of brushed over it is that well, again, we're just rotating the matrix to make the multiplications work. We wouldn't want a 2 by 1 matrix, right? Because otherwise the matrix multiplication would not work, right? Can't multiply 2 by 1. Well, you could, but it wouldn't really work, right? So you transpose your input and then multiply that by the weight matrix. Okay, so moving on to some more application, unless anyone has any questions. All right. So let's kind of go through like a real world data set. So a very famous starter data set is the iris data set. So we have 150 samples of like different iris flowers. So in our case, we have 3 classes, Setosa, Versicolor, and Virginica. And the goal on this data set generally, when people play around with this, is a classification task, right? Can you, taking these 3 features of petal length, or sorry, sepal length, sepal width, petal length, and petal width, can you predict the correct class, right? Yeah. So I have some code over here if you guys kind of want to follow along. If you want access to the code, you could just hop on over to our lectures page and then hop on over to our slides, which take this to the slideshow. And then at the very end of the slideshow, we have the link to the code, right? If you just kind of want to follow along and play around with it, right? You don't have to, but that just, up to you guys. So I'll give you guys a second to do so while I find my place back in the lecture. Right. Okay. So I'm just gonna keep moving. Okay. So primarily at ML UVA, we usually work with PyTorch. So this is a deep learning library in Python that just makes our lives significantly easier. You might have heard of TensorFlow or Keras. Those are alternatives to PyTorch. Functionally, they do the same thing. It's really more of a whatever you prefer. Some libraries or like GitHub repos support, are coded in PyTorch, some are coded in Tensor. So really pick whatever fits your projects. Most of our client projects will probably use PyTorch though. Okay. Notice that we're talking about Python. Most modern day machine learning is done in Python. In the past, it was done in MATLAB, but nowadays it's almost entirely in Python. If you remember the GPU stuff I was just talking about, all of that kind of very low level stuff is done in C, right? C or C++. I believe CUDA programming is done in C++. So if you're kind of working at a high level, building neural networks, training them, that's almost always in Python. If you're trying to like optimize things, make like your make your backprop work a little bit faster, that's done in C, C++. We usually don't work at that level though. Okay, so kind of our data structure for working with matrices in PyTorch is called a tensor. I believe TensorFlow calls it the same thing, right? That's the tensor in TensorFlow. Beyond just giving us a useful representation of a matrix, it stores useful data for back propagation just without you really telling it to. So when you do these matrix multiplications, it stores those intermediate values that make back propagation like a one-liner, right? The way it does this is by storing something called a computational graph. So whenever you do a matrix multiplication, for example, A times B, right? That tensor for A will remember, hey, I was multiplied by B at some point. So that way, when we calculate derivatives, it can work backwards, right? Without you ever having to tell it to really store its interaction with B. Okay. So if we wanted to construct this neural network, we could have as many hidden layers as we want, with as many neurons as we want per layer. Kind of the things that are set in stone in this case, though. So again, this hidden layer stuff is up to our discretion as the developer. The requirements is that we have 4 input features. Remember the 2 lengths and the 2 widths. Um, for our purposes, the order of which does not matter. You could have sepal length, petal length, like it doesn't matter what the order of the inputs are because they're independent, right? And then remember, since we're doing classification with multiple classes, we have 1 output neuron per class, right? Okay. Does anyone remember what the outputs of these should be? Like, yeah, can anyone describe like what the output should look like numerically? Probabilities, right? So for example, it might say 99% this type of flower, 0.05% this other flower, right? That's the goal with classification. We get those nice probabilities at the end. And remember with probabilities, all these outputs should sum up to 1. Okay, so 3 lectures in, we're touching some code. So how many of you guys know what like classes or object-oriented programming is? Okay, so I guess this would be an intro to object-oriented programming very briefly for you guys. So if you focus on this block down here, we call this a class, right? So a class serves as a blueprint for your own data structure, right? And so within a class, you could store whatever methods or functions that you want, like you write your own custom functions, and you can also store your own custom variables, right? So in Python, if I want a variable that represent our first layer, I have self dot. So that just means, hey, this variable FC1 belongs to my class, self dot this variable. And you'll notice that, hey, def forward, that's how you call functions or methods in Python. So the forward method belongs to this class. So that way, when I use this blueprint to create an object or to create my model in my code, I just do model equals, well, the name of my class. And then I could call that function, right? Does anyone notice anything weird about the syntax, right? Because remember, the function that I want to call is forward, right? But I'm doing model parentheses, whatever my input is. What's weird about this? Does anyone know? Like, what should it normally be? Like, what should this line normally be? Outputs equals model parentheses input. Yes. Normally it would be model dot forward, right? So whenever like an object of a class calls its own custom method, it would be object name, variable name, dot custom method, right? And then parentheses input. PyTorch, I guess, out of the goodness of their hearts, um, define some hidden functions for us, right? I believe it's the underscore call method, but regardless, it basically made shorthand behind the scenes that if you just do variable name parentheses input, you effectively call forward. So in other words, they just made a shortcut for us. That's all it is. Okay. If you guys want to do that in your own code, it's underscore underscore call underscore underscore. All right. Anyways, back to the main stuff. So in this first block of our class, this is called the constructor. So this is where we define our methods, like kind of its internal variables. Sorry, our class's internal variables. So we generally define we have a variable for each input layer. Sorry, for each hidden layer. So again, if I want a neural network with 2 hidden layers, I have 2 hidden layer variables. And the forward pass basically defines how our forward propagation step should look like, right? So in this case, I take X as input. If you're new to object-oriented programming, that self is like a must-have. Like you can kind of treat it as like a default starter placeholder, right? Our only input is this X. So in this case, it would be like an input matrix, right? So what we're doing is well, sorry. Yeah. So FC stands for fully connected layer. That's just shorthand term for like a layer in our neural network, right? So in this case, the notation for NN dot linear. Oh, sorry, I think I skipped a slide. My bad. Before I kind of break that stuff down. So whenever you create a custom neural network, you inherit from something called from the NN dot module parent class. So what what kind of inheritance means is PyTorch gave you this NN.module class, which again gives you a template or layout for a neural network. If we inherit from that, we get all those little, nice starter functions for us. So for example, like, the logic for handling those intermediate values in backpropagation, the NN.module handles all of them. Like we don't even have to touch it, right? So all those nice properties are hidden away in NN.module so that you always, always, always must have that here. Yeah. Okay, moving on. So FC1 just stands for fully connected layer 1 and fully connected layer 2. So again, that's that first hidden layer, that second hidden layer. So the first argument of NN.linear, again, sorry, that's just stating the number of inputs that layer has. And the second argument is the number of outputs that layer has, right? So again, in our case, remember, we had 4 input features. So the first layer must always have 4, right? And then notice that the second layer, well, we're expecting an input of size 10. So the previous layer has output size 10. Does that make sense? Yeah, so you can kind of see that, hey, like we take 4 inputs, and the next layer could have as many outputs as we want, right? We just have to, for our final layer, right? So in this case, when we have 2 layers, that final value has to be, well, the number of classes we have, in this case, 3, right? So in other words, kind of these 2 values and the number of hidden layers, that's all up to you. Just be careful that you choose the correct number of input layers for input values for your first layer and the correct number of outputs for your final layer. Okay. Yeah. So, to kind of go through like our forward, again, this stands for like the forward pass of our neural network. We just pass our input matrix through that fully connected layer. So again, that's just doing the X times weights plus biases. Those weight and bias values are hidden inside of this linear function. This linear object. And then we pass that through a ReLU, right? Yeah, so this entire line is passing those 4 inputs, right? So these 4 inputs would be X together. We pass that through our fully connected layer, and then we pass those outputs through the ReLU. Okay, does anyone want to take a guess of how many weights are on this NN.linear? Remember, we have 4 inputs and then 10 outputs. So each neuron has 4 lines coming into it, and we have 10 neurons, right? How many weights in total? 40. We have 40. We have 40 weights in that entire layer, right? So another good way of remembering it is this first number specifies how many inputs per neuron. So in this case, 4 inputs per neuron, right? All the outputs from the prior layer feed into each of the neurons in the next layer. And then that second number just specifies how many neurons we want to have, right? So 10 neurons with 4 inputs, right? Well, okay. And then, so the second layer, so that's kind of this chunk over here. Well, that takes the outputs from the prior layer, right? That X value, and then passes it through the feed forward. In this case, we don't really need activation. So it's just, we just pass it through that feed forward, sorry, that fully connected layer, and then we get our final output out. Okay. Any questions about the code or anything like that? The logic is the same as what we've been doing for the last two lectures, but does anyone have any questions about like syntax, things like that? I know I kind of did like a rough crash course of like object-oriented programming classes. So if you have any questions about that, feel free to stay after, but I highly recommend brushing up on that first, just for like general software engineering, just to make that process easier. Okay. Right. So when we're back in terms of code, we can just create a model. Just by model equals neural network like name, right? In this case, we named our neural network IrisNet. We could name our, so in order to create our loss function, right? Fortunately, we don't have to create that ourselves in Python. We could just import the nn dot whatever loss function we want. In this case, we're using cross entropy loss. And so this is a very go-to loss function when we're dealing with multiple like classification with multiple classes, right? I'll be going over this more in a future lecture. So for now, just remember cross entropy is kind of the go-to loss function for multi-class classification. Okay. Yeah. So yeah, just to briefly go over cross entropy. So review of second lecture. Let's say, so the direct outputs of our neural network, those are called our logits, right? So again, in this case, 2, 1, 0.1, right? We then want to transform those into probabilities such that when we sum up all of our outputs, they sum to 1, right? Again, all we're really doing in between, like in that line, is that we're just making this output more readable, right? Easier to work with, right? There's no neural network, there's no feed forward, none of that stuff. So what the cross entropy then does is it multiplies each output by 1. So in this case, 0.66, and zeroes out all the other ones. And so we do that for, yeah. Yeah. So in this case, the true like output was the first one, right? So we zero out all of the other output values. And our final loss was how confident we were in the correct class. So kind of to reiterate that, right? Since this top class Setosa was our correct value, right? Yeah, it was a correct value. So, yeah. So if we kind of like thought that, like, if we put excessive confidence in a different loss function, sorry.
What's the layer before the loglets?
That's just the ReLU. That's just like our nonlinearity, the max of 0 versus.
Layer between the.
Oh, this one?
Yeah.
That's just like a hidden layer. Yeah, that's just a hidden layer, and that feeds into our upper layer. So, yeah. Okay. So, yeah, any questions about cross entropy? Like, we're basically like isolating how well we did on the correct class, right? So in this case, we didn't do too great on the correct class. So the cross entropy is fairly high. Okay. Nope. All right, I'm gonna keep moving. So generally with regression, right, it's some entropy type loss function. Again, there's a bunch of loss functions to choose from. These are kind of the go-to. When you're only doing like two classes, we have binary cross entropy, which if you just simplify out cross entropy for two variables, it just simplifies to this equation down here. These two are the same thing. It's just cross entropy works with more variables. With regression, like mean squared error, mean absolute error are very common ones, but generally there's like way more flexibility in terms of choosing loss function for regression versus for classification. Most people stick for these two. Okay. Okay, so kind of the third thing that we need to create before we start actually making our training loop is our optimizer, right? So we've learned how to do gradient descent last lecture. And so, but very rarely in practice do we just use gradient descent as is to improve our neural network. So in this case, I'm using something called Atom, which is a improvement upon gradient descent. So it's doing the same process, of, okay, so we have our loss, right? And we're finding out how well or how much each weight and bias contribute to the loss. It's doing the same thing, calculating those gradients. It just does so in a better way, right? So I think we'll cover Atom either in a future reading group or in a lecture. But for now, just think of it as a much beefier, a lot smarter gradient descent. Okay. Yeah, one really good thing about Atom is that it doesn't get stuck at those local minimums, right? So gradient descent would find a minimum, the gradient would turn to 0, and you just kind of stop updating. Atom's more smarter, it doesn't get trapped as easily. Okay, so this is the code for putting all those pieces together. So, we have our model, our loss criterion, and our optimizer. To put them together to actually train our model, we first start iterating through our data. So some terminology, an epoch is the kind of number of times that you've gone through the entire data set, right? So if you say you're on your first epoch, that means you're training your model for like on your entire data set for the first time, right? So epochs, again, are like units of time almost, or units of iteration. We measure them in terms of going through the entire data set, right? Okay, so model.train just tells the model to start. Remember, PyTorch keeps track of gradients and those intermediate values in its tensors. So model.train just tells it, okay, start keeping track of stuff, right? If we always have model.train on when we're not doing training, then it can kind of slow down our process. But generally, it's not too harmful to have model.train on. Unless you're on your evaluation, which we'll get to on the next line. So model.eval is the alternative that tells our PyTorch to like go into testing mode, in which case don't keep track of gradients, right? Again, making this distinction is good practice. It messes up your code in like niche cases, but generally it's not super important, but just good practice. Having model.eval there when you should can speed up your code a little bit. Okay, so within our epoch, we don't always like for up until now, we've kind of just been thinking of doing back propagation on individual pieces of data, right? So we have in like one row of flower information in our data set, we do forward prop and then back prop, and then we do the next line, right? In practice, we usually try to avoid doing that, right? So instead, we group our data sets into groups that we call batches, and we feed those entire batches into our model instead of one data point at a time, right? And so what's the point of doing this grouping operation? Like why send multiple things at a model at once as opposed to one at a time? Well, oftentimes it could help with speed, but especially like, yeah, it could help with speed in some cases by handling data in parallel. But the bigger thing is that it helps with stability, right? So instead of updating a model per data point, like what happens if you have an outlier that doesn't really match the pattern river data set? Like your sensor messed up and like you have an erroneous data point. Well, that data point could push your model's gradient descent in the wrong direction. So by doing things in batches, we can average out those gradients and have a smoother curve. More on batches and gradient descent in a little bit though. So however we choose to break up our data, either in groups of 64 in this case, or groups of 1, whatever you choose to do. That first block is our entire forward pass process. It's just 3 lines, really just 2 lines. Outputs equal model inputs is really again, inputs is that matrix of inputs, right? And then we pass our outputs to our loss function, which takes the labels. So again, labels is like what the true values of the output should be for every data input. And then it just calculates our loss. Again, those 3 lines for forward pass and backwards pass is really 3 lines. The 4th one for logging. Optimizer.zeroGrad. So again, remember, we're keeping track of all the gradients, right? So .zeroGrad like forgets the gradients of the previous step. So, we start on a fresh slate. We still have our intermediate values though, right? So loss that backward does the entire backward propagation process for us in a single line, right? So once we do loss that backward, all of our tensors, like all of our weights and biases, know what their gradients are, right? And then, optimizer.step updates said weights and biases. So loss at backward and optimizer.step, it's just those two lines. Zero, well, you need optimizer.zero grab, but that's more of a formatting thing. All the logic is clustered in those two lines. So yeah, PyTorch makes our lives significantly easier. TensorFlow, very similar process. I would recommend though, this does let us get very sloppy with theory and like logic and stuff. So it's always good practice, like for your first project, to like maybe try doing this without the help of PyTorch. But in reality, just lost that backward. Okay, so kind of going back, by the way, this is like the entire training process. We're done in terms of code. It's like these 10, 15 lines of code, that's it. Very simple. Moving back to batching in gradient descent, what we've been doing up until now is called stochastic gradient descent. Again, the idea of passing one data point through a model at a time and then doing back propagation, right? So again, if our data set has like 15 data points, in this case, I made a custom data set, 15 data points, right? Well, per epoch, again, per pass through the data set, we do 15 forward passes and then 15 backward passes, like, and so we have 15 updates per model, right? So the reason why we don't want to do that is you can notice, so I've plotted the data set here, that it follows a very nice line, right? A very simple data set, but these three samples don't follow the trend. They're like complete outliers, right? And so here I've graphed like the inputs. In this case, our data set has a single input feature, X. Here are like the Y trues. So Y, again, this is not the predicted. This is like in our data set. These are the true values. So you can imagine like whoever's recording this data made a mistake. Or the real world, like in the real world, things are noisy, right? So you could attribute this to noise. So when we calculate our error or our loss, right? All of these are negative, negative, makes sense. And then we got these positive losses, which is like really strange. So when we then calculate our derivative with respect to some weight, let's say W2 in this case, all of these, different magnitudes, which is problematic in its own right, but they're all negative, right? They point in the same direction, except for these three. So when you do your gradient descents, stochastic gradient descent, so you update your model per row, right? Well, when you get to these rows, it's going to push in the wrong direction, right? Which could, by a factor of like 61. Now, your learning rate would kind of mitigate that harm, but still, right? It's pushing in the wrong direction. So the pro of this is, well, uh, assuming you don't have outliers, you update very quickly, right? So like each gradient update you make is reliant on a single piece of data, right? It's fairly fast. So if you're doing stuff on a CPU, for example, on your computers, stochastic gradient descent, like if you do stochastic gradient descent on your CPU versus like doing it on GPU, your CPU won't be that much slower. You're not doing that much stuff in parallel. The problem, as we said, is very sensitive to outliers, so it makes it very unstable. Okay, so the complete opposite of that on the other end of the spectrum is batch gradient descent. So that's when we do a forward pass on every single data point, usually in parallel, right? And so we don't do backward, like we do backward prop after averaging all of our errors. So in this case, we average all of our errors to get -2, and then we do back prop on that -2, right? So with 15 data points, we do one updates. Again, you can think of it as averaging all of your gradients, right? So again, the pro of this, I'll start with that, is that it's very, very stable, right? Again, you're just completely smoothing out your outliers. Over time, you'll probably get to the right answer more likely than with stochastic gradient descent. The con is this is very slow. Even with GPUs, you're still handling a ton of data all at once, right? So unless, like, if your input data is like a million samples, um, a GPU can't handle that much stuff in parallel, right? So it would be somewhat slow. What's more problematic than the speed though is the memory usage, right? If you guys have ever used PyTorch or CUDA, you guys have, or sorry, PyTorch or TensorFlow already, you guys might have gone like CUDA, like out of memory error. Very annoying, right? That basically means your GPU has run out of memory, right? Remember those GPUs have very small caches, right? So, like you basically have to store not just your entire data set in memory, but those intermediate values, those gradients, right? It's not just this data set, it's all that other stuff that your tensors store. So batch gradient descent, it's slow, high in memory, could crash your computer, whatever server you're using, but it's very stable. What is a good compromise? Well, that's what we were doing earlier with batching. So mini batch gradient descents, right? So in this case, we kind of try to get the best of both worlds in that we choose a grouping size or a batch size. In this case, we have a batch size of 5. And we average the gradients and the losses in those groups or batches. So you might have noticed that here, like I've randomized the order of the data. Generally, that's good practice, right? So you kind of uh, get like each batch is meant to represent your entire data set, right? And by randomizing your batches every time, like every epoch, you're kind of getting those nice random samples, right? So again, by taking these batches, the idea is that these gradients are somewhat close, they're approximations of our average out gradient of -2. So in this case, it got the direction right for each of our batches, but like the magnitude was off, right? Like our magnitudes are kind of crazy. So again, you can imagine if I took larger batches, right? Those individual batch gradients will look more similar to our full gradient or full average out gradient. So again, the trade-off here is that your memory usage is as much as you'd like for it to be. You only need to store like one batch in memory at a time, right? Like if you remember from our code, right? We're iterating through every batch, right? So we have this for loop per batch, right? We're not running multiple batches in parallel. We are running all the items inside the batch in parallel. Okay, and it's semi-stable, right? So we are smoothing out our outliers to an extent. So you'll notice that positive value of 61 and that positive value of 73, those do get averaged out. But again, the smaller the batches, the more unstable it gets. Okay, so this is just kind of a formalization of our batch gradient descent. Again, we're just summing up our individual losses. That's little L of I. That's the losses from each data point. We sum them together. That's what this symbol is telling us to do. And then we just divide it by the total number of samples. So in other words, the gradient of our loss is just the average of the gradients of all of our data points. And then we update our parameter, so theta being whatever parameter or weight or bias, by that averaged out gradients. Okay. And again, if you up per epoch or per full data set, you update as many batches you have. Okay, so this is just kind of a summary of our training loop. And again, we were just talking about revising the loss calculation process. So, you can take a look at this on your own time if you want to refresh the process. But again, we break up our data into batches. We do our forward pass. We calculate our loss. Again, these 2 lines are like 3 lines in code. Backward pass, this is 2 lines of code. Well, really, that's 1 line of code. Updating weights is just optimizer dots update. And then you move on to the next iteration. Okay, so again, I already covered the pros and cons of stochastic gradient descent or backprop on individual data points versus using mini batch gradient descent, but this is just here if you guys want that summary. Okay, so just to wrap up, some review in terms of ways of when you're training your neural networks, you guys all have the tools to do that now. If you remember from last lecture, we covered over versus underfitting. So again, overfitting is when your model memorizes like the entire data set. So for example, instead of figuring out that, okay, my data set is following a line, right? Well, your model might accidentally like swoop down and pick up these data points and then swoop back up, right? So that's overfitting versus underfitting is when your model just completely fails to learn the trend, right? So you can identify overfitting when your model does very good on the train set. So, we split our data into the train and test set. When your model does very well on the train sets, but does very bad on the test set, it's overfit. When it does bad on both or just the train set, it's underfitting. It hasn't grasped the pattern yet. Again, we just learned that the batch size can dictate how training goes. Again, smaller batches make the training more unstable, but faster. Larger batches make it a lot more stable, but slower. So the choice of optimizer is important as well. In this case, like for our like for simple purposes, Atom is kind of the go-to. If you were to just do naive gradient descent, like what we covered last lecture, your model would get stuck at local minimums and fail to like be the best it could be. So something we'll be covering more in future lectures, but I still wanted to cover like briefly is the idea of feature selection. So remember for our iris data set, we had 4 input features, right? But what happens if someone made a mistake, give you the data set and give you like 10 useless random features, right? So it's important to have this idea of feature selection. So you train your model on the most useful features, right? We'll be covering this, I believe, next lecture, the idea of the curse of dimensionality. But the idea is that the larger your neural network gets, even if all your features are useful, the harder and harder it gets to train, right? So some of you might be thinking, okay, we have this neural network, right? Rafi told me that, hey, this could learn any function in theory. So why haven't we had ChatGPT like 20 years ago? Well, this idea of the curse of dimensionality of learning, like your neural network being extremely wide and deep, that makes it much harder to train correctly. It makes it significantly more prone to overfitting and underfitting in some cases. So I just want to leave you guys with that. If you guys want to play around with the code, the lecture is up. These slideshows are up. All the codes there, plus some other, the intermediary code. But yeah, thanks for coming to today's lecture. Remember, projects are due on the 30th. If you RSVP'd for the competition, that's the 28th. Otherwise, let me know if you have any questions now or send me a DM or send me a message on Discord. All right.